This research paper, titled Nonlinear Representations and Pre-training Data Frequency in Language Models, explores how the data used to train language models influences their internal workings, specifically focusing on something called linear representations. Language models, or LMs, are AI systems like those powering chatbots or text generators, and they're trained on vast amounts of text data through a process called pretraining. The key idea here is that the frequency of words or phrases in this pre-training data plays a big role in how the model represents and understands concepts. The authors, including Jack Marullo from Brown University and others from the Allen Institute for AI and the University of Washington, investigate why some concepts in language models are encoded in a simple, linear way. In simple terms, linear representations mean that certain ideas or relationships in the model's internal code can be approximated as straight lines in a high-dimensional space. For example, the model might represent the fact that France is the capital of Paris as a direct, predictable pattern in its neural activations. This is important because linear representations are easier for humans to interpret and manipulate, allowing us to understand and control the model's behavior more effectively. Previous studies have shown that not all concepts are represented linearly. For instance, relations like country to capital might be linear for many entities, but something like star to constellation often isn't. The authors wanted to figure out what drives the formation of these linear representations, and they hypothesized that it's linked to how often certain terms appear together in the pre-training data. To test this, they examined factual relations, such as subject-relation-object triplets, like France capital Paris. They looked at two main factors: the frequency of co-occurrence between the subject and object, and the model's ability to learn the relation in context. Their experiments used models like Olmo 7b, GPT-J, which is 6b parameters, and Olmo 1b. They found a strong correlation between these frequencies and the presence of linear representations. Specifically, for a linear representation to form consistently, the subject and object in a relation needed to co-occur at least about 1,000 to 2,000 times in the pre-training data for larger models, and around 4,000 times for the smaller Olmo 1b model. What's interesting is that this pattern held true across all stages of pre-training, meaning it's not just about the model getting more capable over time. Even early in training, if the terms met these frequency thresholds, linear representations started to emerge. The authors analyzed this by tracking how often specific words appeared and how well the model could predict relations based on context. They also discovered that in context learning accuracy, for example, how well the model could guess the correct object for a subject and relation based on examples in the input, was highly correlated with these linear representations. In other words, if the pre-training data had frequent co-occurrences, the model not only formed linear patterns but also performed better on related tasks. Building on this, the researchers went a step further by training a regression model. This model takes measurements of how well linear representations are formed in a fully trained language model and uses that to predict how often certain terms were seen during pre-training. Remarkably, this regression model worked well even when applied to different models with entirely different pre-training datasets. For instance, it could estimate frequencies for a closed-source model where the training data isn't publicly available. The error rates were low, showing that linear representation strength carries a lot of information about the underlying data. This finding opens up new possibilities for understanding and improving language models. By analyzing linear representations, we might be able to infer properties of a model's training data without needing access to it directly. That could be useful for auditing models for biases or ensuring they're trained on diverse, high-quality data. The authors emphasize that manipulating pre-training data to hit specific frequency thresholds could help control model behaviors. For example, if we want a model to have strong linear representations for certain facts, we could ensure those terms appear together frequently in the training corpus. They conclude by noting that this connection between data frequency and representations provides a fresh avenue for research in model interpretability and performance enhancement. Overall, this work bridges the gap between what we feed into language models and how they process information internally, highlighting the power of simple statistical patterns in shaping complex AI systems. The code for their experiments is available online for others to build on, which could lead to more advancements in the field.